Hello everyone, welcome back to Discrete Mathematics and its applications. We continue our discussion on equivalence classes, and we look at now the one interesting property of equivalence classes um, with this theorem. Now, suppose R is a binary relation on A, and actually R is an equivalence relation on A, and let small a and small b be arbitrary pair of elements of A. Yeah, that is A is in A. Now, then we have three statements. Uh, 1, 2, and 3. Right. We want to show that these three statements are equivalent. That is, this holds. Right. The first one is A is related to B by R. Then second one is the equivalence class of A is the same as the equivalence class of B. And then the intersection between the equivalence class of A and the equivalence class of B is not empty. So we show for this, we show that 1 implies 2, and then 2 implies 3, and then of course 3 implies 1. Now let's start with the first one. Let's establish 1 implies 2. So suppose A comma B is in R. Now we show that the equivalence class of A is equivalence class of B. That is, of course, we have this that A equivalence class of B, A is a subset of equivalence class of B, and equivalence class of B is a subset of equivalence class of A. Now, for the first one, we show this, and then after that we show this, right? So for this one, now let C be an element of equivalence class of A. Then, by definition of equivalence class, we know that A comma C must be in R. Yeah. Then by this, C comma A must be in R, since R is symmetric. Now, because C comma A is in R, and then also we know that A comma B is in R. So since we also know that A comma B is in R, so since A comma B is in R, we know that by transitivity of R, we know that actually, well, C comma I and A comma B, so you have that C comma B must be in R. Then by symmetry R, we have that actually B comma C is in R, thus C is an element of the equivalence class of. Yeah, so we have thus the equivalence class of A is a subset of equivalence class of B. Now how about the opposite direction? Next, so we say let C be an element of the equivalence class of B. Then again, this time B comma C is in R. Yeah. And by symmetry we have that actually, well, C comma B is in R. And in addition, also by our first assumption here, we also know that B comma A is in R by symmetry. So by transitivity, this means that of course C comma A is in R, and by symmetry of R again, we have that A comma C is in R, or C is element of equivalence class of A. Thus, we have that actually subset of equivalence class of B is a subset of equivalence class of A as required. So we've shown that actually the equivalence class of A is the same as equivalence class of B. Now, for the next part, the part 2, we're going to show that 2 implies 3. So we suppose that the equivalence class of A is the same as the equivalence class of B, and we show that the intersection of these two classes is not empty. Now this is actually easier because by reflexivity, A comma A is in R and B comma B is in R, right? By reflexivity of R. Now, because of this, obviously A is in, by definition of equivalence class, A must be is in A and B must be is in the equivalence class of B. Thus, equivalence class of A is not empty, and equivalence class of B is also not empty. Yeah. Now, since they are both not empty and they are equal, yeah, they are both not empty and they are equal, then we have that actually the intersection of both is same as A, same as B, and they are all not empty. Yeah. That establishes the fact that 2 implies 3. Now, what about the third statement? Does it imply 1? Now we could show that. So suppose you have that A intersection with B is not empty. Equivalence class of A and equivalence class of B, the intersection of these two equivalence classes are not empty. Then we show that A must be related by R to B. So since the intersection of equivalence class of A and equivalence class of B is not empty, then there is an element C of A such that C is an element of the intersection. Right? Now, this means that C is an element of equivalence class of A, and also C is an element of equivalence class of B. Now, by definition, this means that A comma C is in R and B comma C is in R by definition of equivalence class. Now, by symmetry of R, we have that actually C comma B is in R. And then by transitivity of R, this implies that A comma B is in R as required, right? Because A comma C is in R and C comma B is in R, so by transitivity A comma B must be in R. So we now establish that 3 implies 1. Overall, we established 1 implies 2, 2 implies 3, this statement, yeah, and 3 implies 1. So because of that, we established that the 3 statements are equivalent. Now we stop here and we continue with the next properties of equivalence classes.